In the previous video, we talked about 3 diode models that can be used to approximate the diode terminal characteristics. The first model is the ideal diode model, and in this model we approximate the terminal characteristics of the diode to be, if this is VD and ID, to be like the ideal diode, which means that here it's a vertical line and horizontal line, which means what, or implies what? It implies that if the diode is on, it will operate as a short circuit. Because a short circuit, the voltage will be 0 and the current can take any value, but the current has to be, the current of the diode, it has to be greater than or equal 0. This is the condition. And if the diode is off, it will work as what? It will work as an open circuit, right? But the condition for that, the condition for the diode to be off is that the V diode must be less than or equal 0. V diode must be less than or equal to 0. This is the condition. But if this is off, then it will work as an open circuit, which means that the current is 0 and the voltage of the diode can take any value below 0. When the diode is on, it will operate as a short circuit, which means that the voltage across it is 0, but the current can take any value greater than or equal to 0. The second model is called the constant voltage drop model, where we approximated the terminal characteristics of the diode to be something like this. Same like the ideal diode, but shifted in the voltage. That's why we represented the constant voltage drop model as an ideal diode battery, right? And this is VD, this is ID, and this value is VDO. This is the battery voltage. And this implies what? This model implies that when the diode is on, again it will work as what? Here, when the diode is on, the voltage will be at VDO. It has a value VDO, and the current can take anything. So it can take any value. So that when the diode is on in this region, the diode works as a battery of value VDO. So it works as a battery of value VDO. But the condition is that the current of the diode must be greater than or equal to 0. This is the condition. So when the diode is on, you can represent it as a battery of value VDO, and the current can take any value greater than 0. The condition is that the current is greater than or equal to 0. When the diode is off, which is this region, when the diode is off, then it will work as an open circuit again. It will work as an open circuit. But the condition for the diode to be off is what? The voltage of the diode. The condition is that the voltage of the diode must be less than or equal to VDO. So here, when the diode is on in this region, you can represent it as a battery of value VDO, right? Because the voltage will be fixed at VDO and the current can take any positive value. The current of the diode must be greater than or equal 0. You can consider that this is the condition for the diode to be on, okay? And you can represent it as a battery. Here, you can represent the diode as an open circuit, but the condition is what? The condition is that the voltage of the diode is less than VDO. The third model was the piecewise linear model, where we approximated the terminal characteristics of the diode, VD and ID, by a curve that looks like this. 0 here, and then a line that is not vertical, a line with a certain slope, and the slope of this line, is 1 over the resistance. Since we have a slope here, we represent the model of the diode, we represented it using an ideal diode, battery, and resistor. And the slope of this line is 1 over the resistor. The value here is the battery value VDO, right? This model, which we represented by an ideal diode, battery VDO, and the resistor RD, this model implies what? This model implies that when the diode is on in this region, you can represent it by a battery and resistor. Battery VDO and the resistor RD. In which direction? Opposite, the battery direction is opposite to the current. If this is the diode, you can represent by a battery VDO and the resistor RD. But the condition here is that the current of the diode must be greater than or equal to 0. This is the condition that the diode is operating in the on region, in the forward region. In the off region, when the diode is off, we can represent it again by what? How can we represent a current 0 and the voltage can take anything, any value below VDO? We can represent it by an open circuit again. So we can represent, when the diode is off, we can represent it by an open circuit, right? But the condition is VD is less than or equal to VDO. This is the condition that it is in the off region. So in all the three models, when the diode is off, we represent it by open circuit. But here, in the ideal diode, VD must be less than or equal to 0, while in the two other models, VD must be less than or equal to VDO. In the on region, we represent, here in the ideal diode, we represent the diode with a short circuit. Here, we represent it by a battery. Here, we represent it by a battery and a resistor. But the condition for the on region is that the current is greater than or equal to 0. And here, we use short circuit only. Here we use a battery, here we use a battery and resistor. This table concludes, or it summarizes the assumptions for each of the models. When the diode is off, you replace it with an open circuit, open circuit, open circuit. But the condition here in the ideal diode is that VD must be less than 0. Here VD must be less than or equal VDO, VD less than or equal VDO. When the diode is on, then you can replace it here in the ideal by a short circuit, and the condition is that the current is greater than 0. In the constant voltage drop model, you replace the diode when it is on, you replace it by a battery of value VDO, and the condition is that ID is greater than or equal to 0. In the piecewise linear model, you replace the diode, if you assume it's on, or if it is on, you replace it by a battery VDO and the resistor RD, and the condition that it is really on is that the current is greater than or equal to 0. Which model to use? The question that appears here, the prize here, is which model of the three models we should use? The answer to this question is it depends on the circuit. It depends on the external voltage source that you connect to the circuit. In order to explain this, I'm going to show you these three examples. It's exactly the same circuit, except that in each case we are going to change the source. Here we are using 100 volt, here 10 volt, here 2 volt. And for each case we are going to compare if we use the ideal model, ideal diode model, and the constant voltage drop model. We'll see how it makes a difference to use a high voltage source and a low voltage source, and how it affects the model that we should choose. Let's start with the first one. In the first one, with 100, if we assume ideal diode, then this diode is going to be probably short circuit. It's going to be on in the ideal diode, so short circuit. The current will be 100 over 100, so it will give you 1 ampere. While if you use constant voltage drop model, then this diode is going to be, when this diode is on, it will be represented by a battery. Let me do it. When the diode is on, it's going to be represented by a battery of 0.7, let's say, volt. This is the resistance of 100 ohm, and this is our source of 100 volt. Then the current here, it will be 100 minus the battery of the diode, divided over 100. This is 99.3 over 100, so it will give you 0.993 ampere. Compare now the current that resulted from using this approximation, using the ideal diode approximation and the constant voltage drop approximation. The difference between them is approximately 7 milliampere. 7 milliampere compared to 1 ampere. So the percentage error here, or the percentage difference between the two models, is 7 over 1000, right? 0.7%. 7 milliampere compared to 1 ampere, it's 0.7%. Let's now reduce the voltage source. If we reduce the voltage source from 100 to 10 and you repeat the same process, you will find that the ideal model will give you 100 milliampere current, while constant voltage drop model is going to give you 93 milliampere. The difference between them is 7 milliampere, but now compared to 100 milliampere. So the error here between the two models is 7%. Here it was 0.7%, here the error is 7%. The error increased. Why? Because the voltage source started to decrease, it started to get closer to the 0.7 of the diode. The difference between these two models is the 0.7 volt of the diode. Here we ignore the 0.7 volt of the diode, right? So now, when you reduce your voltage source from 100 to 10, the 0.7 volt of the diode started to be highly effective, right? Because 0.7 is close to the 10 volt, then it is close to the 100 volt. So the 0.7, it's the effect of the 0.7 started to appear here. Let's go one more step. If we reduce the 10 volt to 2 volt, you will find that the difference between the two currents, 20 milliampere in the ideal case, and 13 milliampere, which means 7 over 20, 7 milliampere over 20 milliampere. The difference is 7 over 20 milliampere. This is approximately 33 to 35%. So the error here between the ideal and the constant voltage drop model started to get bigger. Why is that? Because the 0.7 volt of the diode represents a big value with respect to the 2 volt here, right? It represents kind of big value with respect to the 10 volt here. But here, the 0.7 of the diode, it's very small compared to the 100. So here, it doesn't matter which model you use. The 0.7 of the diode, you can ignore it. You can use the ideal diode model. But here, when the voltage source started to decrease a little bit, then you have to be careful. You have to use more accurate models, because the 0.7 of the diode will make a difference here, because it will be compared to the 10 volt and the 2 volt. So this is how you choose your model. You should choose your model based on the external circuit and the accuracy that you want. Now let's discuss the steps that we are going to follow to analyze any diode circuit. So far we talked about the models. How are we going to use the models in order to solve the diode circuits? This slide summarizes the steps. So the first step is, first you have to select the diode model. Which model are you going to use? Ideal, or the constant voltage drop, or piecewise length? And usually in the quizzes, exams, or in our course, I'm going to tell you, use this model for this diode. I'm going to tell you which model to use. Once you select your model, you'll identify the anode and cathode of each diode, label VD and ID for each diode, and then you need to guess. You need to assume the region of operation for each diode in the circuit. So sometimes you'll get circuits with many diodes, right? So you need, for each diode, you need to assume a region of operation. And your assumption here has to make sense. Your assumption has to make sense. What do I mean by has to make sense? You can assume anything. But if you assume anything, random assumption, then probably it will take you longer time to solve the problem, because your assumption might turn to be wrong, and then you will have to repeat the problem again with a different assumption. So the 3 steps that we are going to follow here in order to solve any diode problem after you select the diode model, the 3 important steps, and these steps are not only important for the diode problems, we are going to use them to solve any problem in our course from now on. We are going to use them to solve the diode problems. When we study the transistors, we are going to use them to solve the transistor problems in both types of transistors, the BJT and the MOSFET. We are going to use the same three steps. The 3 steps are assume, solve, check. And these 3 steps I need you to keep repeating while you are walking in the street, while you are sleeping, keep repeating. Assume, solve, check. Assume, solve, check. Assume, solve, check. What do I mean by assume, solve, check? Again, assume is to assume the status of each diode, the region of operation for each diode. You have to assume whether this diode will be on or off. The other diode, will it be on or off? This is the assumption. And as I said, you have to make sense of your assumption to shorten the time. Once you assume the status of each diode, you replace it with the model. So either you replace it with an open circuit if you assume it's off, or you replace it with the model of the on, whether it's short circuit or a battery and resistor if you assume it's on. And then once you replace the diode with the model, you solve the circuit, you calculate everything about the circuit, and after you solve and you calculate everything about the circuit, you have to check. How to check? You check by checking the diodes that you assume that they are on. You have to check that their current is greater than or equal to 0. And this is the condition that we talked about. If you assume that the diode is on, their current must be greater than or equal to 0. If you assume that the diode is off, you have to check that their voltage, the voltage of the diode, is less than or equal to VDO. So this is how you are going to do the check. For the diodes that you assumed on, you have to check that ID, their current is greater than or equal to 0. For the diodes that you assume to be off, you have to check that their voltage is less than or equal VDO, the threshold voltage. If you find, after you check, if you find that everything is okay, the check is correct, your assumption is correct, then you solve the problem. That's it. That's it. You solve the problem. If you find that for all the diodes that you assumed on, the current is greater than 0, and for all the diodes that you assumed off, the voltage, their voltage is less than or equal to VDO, then that's it. You solve the problem. But if you find that one of the diodes, even one of the diodes in the circuit, your assumption was not correct. For example, you assumed that the diode is on and you found that its current is not greater than or equal to 0. This means that your assumption was wrong. Or for example, you assumed it's off and you found that its voltage is greater than or equal VDO. This means your assumption is wrong. In this case, you have to go and repeat the 3 steps again. Assume, solve, check. That's why I said your assumption has to make sense. Try to make a sense of your assumption so that you shorten the time. You make the time that you solve your problem short. Otherwise, if you just throw any random assumption, then it will take you many repetitions in order to reach to the correct solution. Okay? So you will keep repeating assume, solve, check, assume, solve, check, until you check and you find that everything is okay, all your assumptions are correct. In this case, you stop and you reach to the solution of the problem. In the next video, we are going to see some examples on this. See you in the next video, inshallah.